Hello and good evening. My name is Brent Iverson, and I'm the Dean of the School of Undergraduate Studies, as well as being a longtime chemistry professor here. It's my pleasure to welcome you to the spring edition of the Helen and Jeff Herbert Family University Lecture Series, brought to you through a generous gift from Helen and Jeff Herbert. Thank you, Helen and Jeff, for helping to make this possible tonight. Long, long ago, in a school far, far away, well, okay, it was Caltech in Pasadena, two future UT faculty members met for the first time. It was on an ultimate Frisbee field. The year was 1986. I was graduating with my PhD in chemistry and attending my last ultimate Frisbee team practice before heading to San Diego in the Scripps Research Institute. Jay Banner, an absolutely awesome ultimate Frisbee player, by the way, was just starting his postdoctoral studies at Caltech, and he showed up to our weekly practice. Immediately, I could tell he was going to be a great addition to the team. This guy could really toss a disc. Little did we know at that moment that he and I would be lifelong colleagues and good friends at the University of Texas at Austin. So my first take-home lesson, be extraordinarily nice to everyone you meet during your education journeys. One never knows who's going to be important to your future. Tonight's topic is about climate change, presented from a geologist's point of view. Although this topic is political to many, political arguments are for a different forum. Climate affects us all, and a changing climate will be more important to all of you out there listening to this tonight simply because you're younger than I am. With a topic of such importance, it's essential that each of us understands the very best of what science is telling us. That's why we invited an expert. I also hope you learn a second powerful lesson about making a difference tonight. Apart from his work as a geologist and rock star status as a teacher, Professor Jay Banner has had an immense impact on generations of K-12 students in Austin. He is behind the Hot Science Cool Talks program that brings famous scientists, many of them are UT's Austin's most world-renowned faculty members, directly to any interested student from the local schools. These are extremely well-attended, filling large auditoria on campus and around Austin. I've personally been to several of these, and they are incredible. He also runs the Scientists in Residence program that partners STEM graduate student researchers here at UT with K-12 teachers. Amazing. Here then is your second take-home lesson. Do something, don't just complain. While many of my scientist colleagues endlessly complain that not enough people in our communities understand the latest science, only Jay has spent considerable time, energy, and brilliance in working on a solution at scale. Dr. Banner, you're one of my true heroes. Before we begin, I want to remind you that during the talk, you should be sending me questions for Dr. Banner by hitting the Ask the Professor area of your screen. After his presentation, I'm going to be asking him your questions. Now, on to our presentation. Jay, it's all yours.
Thank you, Brent, for that very kind and embarrassing introduction. I really appreciate it. And also thanks to UGS and the Herberts for creating this lecture series. Hey, everybody. I'd like to talk to you tonight about climate change in Texas using the perspectives of multiple timescales. One key takeaway that I'll present is that climate in Texas is already changing, and it's going to be changing this century in ways that are unprecedented, anything we've seen before in any historical record. So let me start with going through an outline of what we'll talk about. I'd like to start with just what some of the basic predictions of climate science are based on a warmer atmosphere that we're going to be experiencing this century and beyond. I'll also define this term called the 100th meridian climate boundary, first coined over 100 years ago by some very prescient person. And then we'll reconstruct past climate and project future climate change. We'll talk about the basics of how that is done, and then we'll apply it to Texas. We'll talk about Texas climate change and population change and how it all together will impact our water resources, our economy, and other sectors of our society. And time permitting towards the end, I'll also get into a little bit about science and policy in Texas. Those two words there are in the same sentence fragment. Doesn't often happen. So hey, let's begin and talk about what does climate science predict as a consequence of a warmer atmosphere? So what I'm going to show you here are some basic tenets that come out of the Intergovernmental Panel on Climate Change, global body putting out a report every 4 to 5 years, and the US National Climate Assessment, which does the same thing focused on the United States. Altogether, this represents the consensus of over 1,000 scientists and experts in this field. So I think it's often important when we hear about things regarding climate change. Is it really happening? What's the cause? Whose fault is it? What should we do about it? There's sometimes an awful lot of debate. But what I want to go through now are some basic principles of physics and chemistry that can be applied to the climate system. And these principles are not anything that anyone debates about. It's often very useful to have some takeaways and resources like this written as a consensus of the scientific community, but also introduced and summaries provided in very plain language. So I find it a useful resource even for people who are not experts. So one of the first predictions of a warmer atmosphere, if we warm the atmosphere, then the surface of the ocean will warm and there'll be more evaporation over the oceans. Well, that'll put more water vapor into the atmosphere, and all other things being equal, that will lead to more intense rain events. Now, another prediction is if the atmosphere warms, there'll be more evaporation over land. That is going to lead to longer and more intense droughts because the high rate of evaporation will rob the soil of its moisture, and that can trigger droughts and make droughts more intense than they would be otherwise. And finally, if we warm the atmosphere, as we said, the ocean surface will warm. The high sea surface temperatures are sort of one of the metrics of the fuel in the engine room, if you will, of intense tropical storms and hurricanes. So that as sea surface temperatures climb with a warmer atmosphere, we can anticipate more intense tropical storms and hurricanes. And this is a basic principle of thermodynamics. So given all of this, what I'd like to do now is get into something a little more specific. And what I'd like you to do is I'd like you to close your eyes and conjure up an image of North America from space. So imagine you're flying the space shuttle looking down on Earth, or maybe you're Sandra Bullock in that movie where she played an astronaut hanging from a satellite. What was that, Gravity? So imagine you're looking down on Earth and come up with an image of what North America from space looks like. All right, I'll give you a moment. Okay, does it look something like this? Because this is typically what we intuitively come up with, right? This is a composite satellite image of North America from space. And what we intuitively probably came up with, all of you, I bet, is that, yeah, the southeast part of the US is humid. It's humid and lush and wet and green. And as we go to the southwestern part of the US, that's much more arid. And there seems to be a boundary running somewhere right down the middle of the country. That's sort of the dividing line between the two. It's not a very specific, you can't stand on one side of it and take a step on the other side. It's a transition zone. But there is this wet-dry gradient, or what we might call the wet-dry line, or we're going to call it the 100th meridian. Because if you drew that line right down there, 100 degrees west longitude, AKA the 100th meridian, is a pretty good approximation for the modern day position of this wet-dry line. And if you look really carefully and can follow my cursor, I'm mapping out the edge of the Balcones escarpment here, or the hill country to the eastern and southern edge of it. And now I'm drawing a line that's the Colorado River. X marks the spot, so Austin's right there where my cursor is. Right on, so the 100th meridian. What I'm going to show you is evidence that this wet-dry boundary, the actual line of longitude doesn't move, but the 100th meridian is used euphemistically as the position of that wet-dry line. And I'm going to show you some evidence, some data that shows that this boundary has shifted significantly to the east for significant periods of time in the past, and will do so according to model projections into our future. And that is going to bring some very significant consequences to our region. Texas already sits, if you will, in sort of a climate hotspot because the arid southwestern US is prone to droughts, and Texas makes up the eastern edge of the southwestern US. So we have to deal with those extended droughts and being in this kind of region. But also Texas is right on the Gulf Coast. So as a result of that, we experience tropical storms, hurricanes, flooding, etc. So it's kind of a bittersweet climatological spot that Texas sits in, and it behooves us to understand what changes are in store for us because they may have very significant impacts on how resilient our future will be. All right, so let's zoom in on Texas from here. Also a satellite image, and this is using satellite data to get a fix on the health of vegetation. And what you could see is that areas that are very green and lush, the vegetation is healthy. Areas towards the west that are kind of brown, the vegetation is not so healthy. Where it's white, the vegetation is absent. And if you come down right off the eastern line of the panhandle, that is the 100th meridian. So you can see that it was actually a pretty good boundary. Look at how closely, as we zoom in on Texas, that 100th meridian approximates that wet dry line. Okay, this was the end of August in 2010. I'm going to roll the clock forward 365 days, and we're going to go to the end of August 2011, 1 year later. That is a dramatic change in the vegetation health. This was the first year, this was a drought, the 2011 drought, which lasted for 3 more years after 2011, was one of the most significant droughts in terms of intensity in our history. It caused a lot of economic hardship, which we'll talk about in a moment, and it was widespread across the state. And it peaked in this year, and as we go back and forth, we could see that is a very significant shift in this dry line. And I could do this till 8 o'clock, but I know our time is limited. I'm just fascinated by this. But in all seriousness, this has very significant implications for us, because while this was just a relatively short-lived but intense drought, it may be a harbinger of things to come, and it may be a modern example of what we've experienced in the past, both more intense and longer in duration. Well, then I'd like to actually now turn to how this term, the 100th meridian, came up with, and it was coined by this gentleman on the right, John Wesley Powell. He coined this term. John Wesley Powell was a professor of geology at Illinois Wesleyan University. But if you went to see him during his office hours, he probably wasn't there, because he was exploring the western US for much of his career on horseback. He led the first research expedition down the Colorado River and the Grand Canyon on rafts. And he actually came up with this perspective that we can gain now from satellite imagery. Pretty sure he didn't have those back in the late 1800s. He came up with this perspective that the land west of the 100th meridian, he warned people, it just does not have the water resources to support extensive development. Because at the time, we were all about developing westward ho and developing the western half of the US. And he would talk to whoever would listen, including Congress, and he said things such as, gentlemen, you're piling up a heritage of conflict and litigation over water rights. There's just not enough water to supply the land. Well, unfortunately, Powell's voice was not as loud as others, including the large railroad companies, which were given hundreds of millions of acres in exchange for developing the land out in the western part of the US. So they had a very vested interest, a very strong lobby in making sure that that land was developed. And as we know, it turns out, it has been developed. There are many large urban centers in many water-stressed regions in the western US, and there's many issues of, will there be enough water in the southwestern US, for example, as we go into the 21st century. This is a very, very stressful time that will only become more so as we move forward this century, according to the model projections that I'll show you. Well, so that was about 150 years ago, but isn't it settling now to know that here we are, modern day, we no longer have to worry about the undue influence of large corporations on how land is used in this country. Okay, I said that a little bit sarcastically, and I'll move on to tell you that John Wesley Powell was actually quite a guy in many ways, aside from his prescient projections of the water situation that we now find ourselves in. For example, he founded and was the first director of the U.S. Bureau of Ethnology. He led the U.S. Geological Survey. He was an officer in the Civil War, and there he was in the Battle of Shiloh, extending his right arm, giving his troops the order to charge, and he took on musket fire, and he lost his right arm, as you can see in the picture here. Not enough of a hero was he, that he healed up, re-upped, re-enlisted, and he was back in the service, and there he was in the siege of Vicksburg, hunkered down in the trenches that had been dug out to protect themselves from musket fire, and like any good geoscientist, he studied the strata on the walls of the trenches. So prescient was John Wesley Powell that I think with his hydrogeology, with his climate shifts, etc., I think maybe he was also very fashion forward. Look at that hipster facial hair. And I think if you want to know what the best next fad is, I would invest, if you can find them, pants where the waistline is 12 inches above the belly button, because I think that will be the next big thing. All right, well, so enough with my mild obsession about John Wesley Powell, But let's actually move on. And we proposed to the National Science Foundation a project called the new 100th meridian. In other words, the line of longitude won't shift, but if this wet-dry boundary shifts, look what's lying in wait for it. In gray are all these counties where there's greater than 75% population growth between 2010 and 2050 projected. In fact, you could see that the state of Texas's population will double between 2010 and 2060. The demographers tell us that almost all of these new Texans will be moving into existing cities and expanding them outward. So here we go from to the south, RGV, Rio Grande Valley, to San Antonio, San Marcos, Austin, and Dallas-Fort Worth. So that's what's lying in wait for the potential future eastward shift of the 100th meridian. So think about this. There'll be twice as many people. The demand for water in the state will go way up. If this boundary shifts to the east, the available water due to extended drought will go way down. That is not a recipe for a resilient future for us. So we need to be able to look forward and consider how we can be ready for these changes. So let's consider now climate change through time. And when we talk about, let's just go through a little bit of terminology. When we talk about the present climate, we're talking about the instrumental record. Thermometers, rain gauges, those are the kinds of instruments that have been around for about 120 years or so. We get back to the late 1800s, the instruments weren't that good, the record keeping wasn't that good, people weren't worried so much about recording the climate. As it changed every day or year to year, there are more important things occupying their attention. So before the instrumental record, before 1900, we have to have something as a stand-in for what climate was like in the past. And what tells us this? These are proxy records, everything from sedimentary rocks, corals, ice cores, speleothems, tree rings. For tonight, we're just going to focus, I'll share with you data for tree rings in this region that goes back 1,000 years that give us a proxy for past climate. And when we talk about future climate, we're using model simulations. Not me, but my colleagues use these complex numerical codes that simulate how the atmosphere circulates, how the atmosphere interacts with the land surface, how it interacts with the ocean surface, and how things change with time as you spin this model up and go forward. So for example, we could put into the model different scenarios for how much carbon dioxide will be in the atmosphere as a consequence of carbon emissions from how we use energy. Right? So we can project forward a very carbon-intensive energy future or a greatly reduced carbon emission future. And we could run the models under both those scenarios and see what difference it will make. And this could actually help us craft policy. So these models are very useful. At the same time, all models have great uncertainties associated with them. As long as we understand the limits of those uncertainties, they can actually be very useful in characterizing what we may be able to anticipate for our future. And this will be very important for us to take steps towards mitigating and adapting against those changes, adapting to those changes that are coming. All right, so let's actually look at how we reconstruct past climate in one way. Tree rings, as you can see here, you probably are all familiar with this, right? A tree, if you slice it open, the oldest rings are at the center, the youngest are at the margins. And this is just a cartoon. Now I'm going to show you in the next slide a microscopic slide through a tree core. And that's what's shown here. And the oldest part is in the lower left. The youngest part is in the upper right. And I'm going to go through from oldest to youngest, and I want you all to tell me when to stop when I get to the wettest part of the record. Here's going forward. Okay, I didn't hear anybody, and Dr. Iverson's not telling me anybody's saying stop. So, okay, well, all kidding aside, I'll just go through it right here. And when we get to right here, the thickest tree rings are, all of the things being equal, recording past periods when it was wettest. And the skinnier rings tell us when it was drier and when there were droughts. And in this way, we can reconstruct available moisture and droughts going back before the instrumental record. And this will prove very valuable for us. So that's how we take a glimpse into the past. Let's see how we take a glimpse into the future using climate model projections. And we'll do this in the case for Texas. And these results are going to come from the late 21st century, so the last 3 decades of this century, from this 4th National Climate Assessment that I was one of the co-authors on. I had over 300 co-authors. What you could see along the bottom is the legend, the change in the number of 100-degree days. So what that means is there's going to be an increase in the number of days where it's 100 degrees Fahrenheit or hotter. This is saying how, for a given region, what the change will be. And what we could see here is we're looking at Texas, Oklahoma, and Kansas from south to north. And if we go here into central Texas, you could see, looking at that color corresponding to the legend, that looks like it's between 80 and 90 days, more of 100-degree days. If we go back this past decade, we average about 40 100-degree days a year. So think about that, 40 plus between 80 and 90. Let's just make it 80. 40 plus 80, that's 120 days where it's 100 degrees or hotter. What will that be like? I know if I go 4 days in a row where it's 100 degrees, I'm miserable. But putting my misery aside and putting aside some of the very major public health consequences there'll be of such high degrees of heat, we also have to consider what this is going to do in driving evaporation, leading to more extensive droughts, wildfires, etc. There will be some very significant consequences of this. And this model projection is done under what's called the high carbon emissions scenario. In other words, if we continue to use fossil fuels in the intensive way that we have been using them, and we continue to use them, that's what we're looking at. But it's also important to consider the models that simulate a low carbon emissions scenario. How do we get a low carbon emissions scenario? Well, changes in our energy infrastructure, changes in technology, changes in policy that might drive them, and personal changes that we can all make. So that's requiring corporations, governments, individuals to all work together. No one said it would be easy, but it's doable. All right, so let's take a look at the consequence of a low carbon emissions scenario. So temperatures will still rise, there's no escaping that, but it'll be a much different picture of what Texas will look like in the late part of this century if we do go to the low carbon emissions scenario. So for me, an important takeaway from this, and hopefully it is for you, is that you often hear, you know what, we're too far gone, right? All the things that are going to change climate have been set in motion. It's too hard to stop. And I say, graphics like this, data like this tell us that that's not the case, that there actually is the ability to affect significant change. All right, and I would also note that the high emission scenario is often called the business as usual scenario, because that's conducting our business as we always have, which is much closer to the scenario we are presently tracking than the low carbon emissions scenario. So the right is what we have and what we're on track for. The left is what we can hope to attain. So I've read a number of research articles in my career, and that's not bragging. I've read just like way too many peer-reviewed literature. It's just what we do, of course. And this article I read several years ago really caught me. There was one word in that title that really caught my attention. I wonder what you think, which word that was. What was the word unprecedented? What do they mean by that? That sounds almost dramatic. Why, it's unprecedented, never heard of before. And this is in a peer-reviewed science article. Scientists are supposed to be calm, cool, arm's-length arbiters of impartial arbiters of the data. So what's meant by this term unprecedented? I thought that was pretty unusual. And I'll show you data from that study and from a study that I and some colleagues did several years later in going from looking at drought risk, not just in the American Southwest, which is what this article was on, but one that focused on Texas. And there we found ourselves using that word that struck us all as so odd. And there we were using it because our results were quite consistent for Texas with what was seen for the larger Southwest US. And so let's take a look at what these data are that lead us to say this. Okay, so this is a record of the last 1,000 years and projections going forward in this century. So along the x-axis, we have years going from the year 1000 to the year 2100. Right, on the left-hand y-axis is a drought index. You don't have to worry about the actual numbers, but on the right-hand y-axis is telling you what's really happening. Down, negative numbers means dry and drought. Up indicates wet times. And we could see that we could infer when there are periods of drought, when the numbers like here back here go quite negative. And there's also a time here in the 1950s where we had a 6-year drought in Texas. That was during the instrumented record, the most intense drought. If we go back to look at the 1100s and the 1200s, this was almost, except for this one wet period, this was almost one continuous drought. So the width of those troughs below the 0 line tell us how long the drought was. How negative it goes tells us how intense the drought was. All right, well, where do these data come from? Well, the brown curve is the proxy record, the tree ring record going back to 1,000 years. And when we come into 1900, that brown curve is taken over by the instrumental record, thermometers, rain gauges, etc. And now let's bring in this multicolored set of curves. These are model projections. So 17 different climate models or intercomparison projects, CMIP, Climate Model Intercomparison Project, comparing global models from all different laboratories around the world that construct their models looking at the climate system. And there are some slight differences, and we could talk about the vagaries of what makes some models not exactly the same as other models. There's uncertainties in our full understanding of the climate system. But what's important to see here is the gray uncertainty window around those different colored models, right? The different colors are the averages, and the gray bars are the interquartile uncertainty between them. Given that significant uncertainty, what we can conclude from this and still extract from this is that in the second half of this century, even given that large uncertainty, we will be in a very different climate state, one of very intense and prolonged drought relative to what we looked at in the instrumental record and relative to what we looked at in the entire 1,000 years of proxy. So in the entire historical record, do we see anything as big? Well, let's go back to the 1100s, this big, intense and extended drought I talked about here. If that's the worst case scenario in the historical record, then I'm just drawing a line across and we could see that we're already there, and according to the model projections, and we'll be far exceeding it in terms of intensity and length of droughts going forward. I would also note here a very important comparison to make. This is that 1950s drought in the instrumental record. That's called the drought of record. That's used by the state of Texas for planning for its water resources 50 years out into the future, right? It's charged, the Texas Water Development's charges to make sure there's water for all Texans for all purposes 50 years out into the future. And what the planning process that the state undergoes is that the worst case scenario in your planning is make sure there's enough water should the worst case scenario reoccur. And the worst case scenario that's used is this 1950s drought. So I ask you, is this sufficiently resilient planning? Are we doing a sufficient job of planning for our future? Well, I might point to a recent Netflix movie called Don't Look Up, and say that what the state does in this case is it's not looking back, it's not looking forward. It's just using the 20th century instrumental record. And I think we have to move beyond that to look at the full scenario of what we may expect and be ready for in the future. So what are the costs of climate change in Texas? Right? There'll be droughts, there'll be heat waves, there'll be impacts on our water systems, there'll be impacts on public health systems. But let's just look at some pretty basic ways to calculate these costs. So if we looked at these various drought periods and how long they were, there's the 2011 drought I talked about at the outset, there's the 1950s drought I talked about, and these are in today's dollars, 8.7 billion, 3.5 billion, and there's that 1100 to 1200 multi-decadal drought that actually a lot of archaeologists and anthropologists believe led to the demise of the ancestral Puebloan civilization in the Four Corners region of the Southwest US. And then we're looking at that projected 21st century drought. And that is the real question mark, is what will those costs be? And I'll point out that these costs, while they seem large, are not even as large as they might be if we considered some of the full costs. What do I mean by full costs? Well, these costs here are actually calculated based on the loss of livestock and the loss of agricultural crops. But if we consider other services that are lost due to the demise of some ecosystems, for example, the state during the 2011 drought lost 300 million trees. So if we factor in all the ecosystem services that, for example, trees provide, then all of a sudden the costs start to climb. 40 billion for the 2011 drought, not even counting public health impacts that are to come this century. Well, if we consider Hurricane Harvey, it was much shorter than those long onset droughts. Now we're starting to become, 40 billion is starting to become in the same ballpark as Hurricane Harvey, which gets a lot of attention from the media, as well as it should. And those images and the experiences that many of you probably have are probably, etched in your minds and not to be forgotten, because that was a very intense, it was a very costly event in terms of economics, in terms of life, in terms of property. Oftentimes these droughts, since they're slow creeping and it takes a long time before they're on top of you, we don't appreciate what the costs of them are as much. But both of these are equally important. These kinds of extremes in the climate system are very important to consider as we go forward. Here's a lot of unprecedented climate events and impacts in Texas. I don't mean for you to read all of them. First you could say, okay, that's a lot of things. And there's that word unprecedented again. Maybe that means because now they've been happening like in the last decade and they haven't happened in recorded history. We're setting new records all the time. So one of those that I'll point out is in 2018, it was a very wet autumn, particularly October, and that increased the turbidity in the Colorado River, and that increased the turbidity in the intake water into our water treatment plants that for the water utility that serves our city. Cleans up the water, pumps it all over the city. It wasn't clean enough, so we had a 6-day boil water notice as a result of that, right? And not too hard in our rearview mirror is we now have 3 of those in the last 4 years. But before that 2018 boil water notice, there had not been one since the water utility was built. The water utility in Austin was built in 1926. So that meant for something like 90 years, you just turned on your tap and you reliably got drinkable, healthy water out of that tap. But now we can no longer count on that, in part because of these climate extreme events that we're seeing. So let's just simplify this and categorize these things. We've had record water shortages in the last decade. We've had record rainfall between Hurricane Harvey and that 2018 event, autumn I talked to you about. We've had record heat, right? The hottest 8 years on record in the world have been the last 8 years. And there have been more intense tropical storms and hurricanes. So I pose this question to you. All of these unprecedented events, all of these varying in nature, too much water, too little water, high heat, how do any of these fit with what climate science predicts about the effects of a warmer atmosphere? This is what we talked about at the very outset. Remember, based on the laws of physics and chemistry. These are all fully consistent with those predicted effects. Now, this does not prove that any one of these events is a consequence of human-induced climate change. However, altogether, they are fully consistent with what climate science predicts. Well, and here's an image of back in 2018, that boil water notice. These are lines for bottled water from Costco in South Austin. And I'm not sure if you could see it from your perspective, but the lines here to get into the store starts here. It snakes all the way back down as far as you could see the trees, and it wraps around and comes all the way up this way. People waiting for hours online, having to order had to be kept by the police. And I ask us as we go forward between climate change and the state of our infrastructure, sometimes we have to ask, what are we aspiring to be? A developed country, a developing country? I think there are also some very important consequences of this that may go unappreciated. For example, there's a real issue about environmental justice here. A family that's of low socioeconomic status, that has both parents have to work multiple jobs and they can't afford childcare, do they have hours to stand on line for bottled water? So the environmental justice connotes when the impacts of environmental change are disproportionate towards underserved and underrepresented groups. And this was one example of that. So as we start to wind down here, I want to share with you my experience with climate policy at the state level. And so I am not a policy expert. I was drawn into this by being invited to testify on some bills that had been introduced to the Texas State Legislature. As you know, the state legislature meets every other year, and it was in 2009 that the first bill of this kind was introduced that I was asked to testify on, Senate Bill 988. And this, in summary, this bill would require 14 state agencies to take climate change into account in their planning. All right, what agencies are these? Well, some examples. The Water Development Board, which I talked about earlier, Parks and Wildlife, the Texas Commission on Environmental Quality, Public Safety, Utilities, etc. These are all agencies that you think have a strong interest if climate is changing because it's going to impact their work. Well, I was told to be there at 8:30 a.m. sharp. I was actually there and wearing a jacket and tie for the first time in a long time. I was on time and dressed well. And it was 6:30 p.m. that I was called up. And I won't share with you everything I learned about how the legislature works in that day that I sat there waiting to testify. But a couple of things I did learn was every bill has to have a fiscal analysis, right? Because if you propose something and it's going to cost the state $50 million a year, it's not going to, and you can't identify where those funds are coming from, that bill is not going to have much of a chance. Well, the fiscal analysis showed that this bill would require no new costs. Why? Because all of these agencies have as part of their charge planning. That's what they're there to do, regular planning. And all this was saying is when you're doing your regular planning, make climate change one of the things you take into account. Seems like a lot of people that I talked to said, wow, this is a great start. It's pretty innocuous, but it's a great first step to take. And so, as I said, I was asked to testify, and there's a video here. In the interest of time, I won't play the video, but I was told to keep it to 4 minutes, and I basically talked all about the data of the past, the present, and the future projections that I've shared with you over the past half hour. And so you may be asking, well, why didn't you just give it to us in 4 minutes? Well, I don't know. I felt there was more detail I wanted to share with you. But in 4 minutes, I shared that. And without going through the testimony, I want to share with you the outcomes. So that bill was introduced in 2009. And then in 2011, 2013, right? Every year that the legislature met, 2015, 17, 19, 21. They all failed. And the planning for our water future in the state continues to use that 1950s drought as the worst case scenario, as the drought of record. And I pose the question again, is this sufficiently planning for the resilience of our state? And for me, it seems we have to find a way to move past this. I could also share with you experience federal level climate policy, but in the interest of time, perhaps I'll save that for the questions. And I want to share with you some takeaways here. Texas's climate has changed in the past, and it's projected to change in unprecedented ways this century. And at the same time, our state's population will double. This will drive synergistic impacts on water, energy, health, food, economy, social equity. And this is going to require new research, education, policy, and economic approaches in order to address these challenges that our state faces. And what starts here changes the world. The changes that we find in Texas will probably be sooner and larger than in other areas, but what we can learn and understand here will certainly have applicability beyond our state. And so I want to leave you with a question that I'll answer in a few different ways. You may be asking, what can I do during my time at UT in this regard? Can I make a difference? Short answer, yes. Let me give you some examples. So you can get involved in student groups. I'll give you just a few examples. There are many. Campus Environmental Center, Engineers for a Sustainable World, the Division of Diversity, Community Engagement is volunteer projects that a lot of them have to do with environmental justice. And studies have shown that students in these groups are unusually happy and have very above average gleaming smiles. So this could rub off on you. In all seriousness, you can select a major or a minor that's relevant to this. There's a BA degree, there's a BS in the sciences, there's a BS in engineering, all around the environment and sustainability. There's the bridging discipline programs in the environment and sustainability to help you craft a minor custom fit to what you're studying. So you may feel like, wow, what I'm majoring in has nothing to do with this. Well, talk to the people in the BDP program. They'll work magic to make it work with your degree. And you can find more information about all this in this web portal, and I'll post this URL up at the end here. You know, the other thing you could do at your time at the university, you can get involved in research. Many undergrads undertake research at the university. And I just want to share with you some of the expertise of just a handful of my colleagues. I'm going to show you a few. There are literally dozens and dozens of colleagues across every department in the university whose work bears on these issues in some way. So Dave Allen, who I co-teach a UGS course called Sustaining a Planet with, he is an expert sleuth in finding out where methane, a greenhouse gas much more powerful than carbon dioxide, how it's getting out into the environment. He's a detective helping to solve this problem, to help mitigate against future climate change. Geeta Prasad in geosciences, she's an expert in numerical modeling of global climate change and how we could use the model results to understand societal impacts. Juliana Felkner in the School of Architecture. If our population is going to double in Texas, we're going to be building out a lot new land. We're going to be building a lot of new neighborhoods. Juliana's expertise is how can we design these neighborhoods and build them so that they have a much lower carbon footprint than the neighborhoods we currently live in. Go ahead and email any of these guys. They'll welcome it. The other thing you can do in your time at UT is to be optimistic and be engaged. Thanks very much for your attention. Be happy to answer questions you may have, and here are some resources you may find of interest.
Thank you, Jay. I want to get started with some questions, but those of you who actually saw the presentation last night know that I'm going to make a parallel here, and that is that it's really important to get involved in research, but I don't think it's people who are our age who are going to fix this problem. I'm really counting on the people who are watching this to get involved, take action. They're the solution. Don't wait for us. And I think that's an important point. That was true with what we were talking about last night as well, misinformation online and how do we deal with that. Okay, so I'm going to start with a question that it was actually the first question asked. And it was right from your introduction and all the way through the end. I think it's still a great question. And that is that if we're going to see more intense rain events and more intense drought, why don't they cancel?
Yeah, great. Well, in an ideal world, they would. It would be all mass balance, right? There's no water being exported from the planet or being imported from outer space. So yeah, ideally, but it's the challenge is predicting the distribution of that rainfall. So the models do a pretty robust job of projecting the changes in temperature because it's the greenhouse effect. This is a simple knowledge of physical chemistry. A benchtop experiment can reproduce that. Arrhenius calculated the greenhouse relationship in 1908. Really, really well known. So there's some robustness to the temperature, although there are uncertainties on them, but predicting where rainfall will be distributed is much more challenging just because of the nature of the models and the randomness, the stochastic nature of how the atmosphere distributes rainfall. That's part of the issue. So if we're moving regions to becoming more prone to these extremes, the droughts will be longer, the floods will be more intense. And so if we're going to have a mega drought, which is a term we give for a 10-year or longer drought, and it's not raining during that time, that's going to be a big problem. And then if we go into a regime where we have years in a row of excessive rainfall, floods, tropical storms, we don't have the water when we need it. We have too much when we don't need it. We don't have enough when we need it. But there are some technologies being developed here in Central Texas, including in the Edwards Aquifer, called aquifer storage and recovery. So what aquifer storage and recovery does is during rainy periods, we divert some flows during high stages of rivers, just make them take a left turn, or at least part of it, into some of these big sinkholes that are limestone karst terrain, these big caverns. Have it go right down and recharge the Edwards Aquifer. So it's sort of like putting money in the bank, putting water in the bank and raising the levels of the aquifer so that when we then enter into drought periods, we've got that water underground and it lasts longer underground because it's not prone to evaporation or running off into the oceans like surface water would be.
That's awesome. Okay, this question really gets to the heart of conversations that you hear around climate change. So it's going to take a while, but I'm going to read it. Is it true that the Earth naturally undergoes climate swings between ice ages and thermal maximums? If we are in the middle of one of these climate swings, is global warming caused by humans truly significant? Not to say that humans don't cause global warming, but are they the biggest driving factor behind the current climate swing?
Right on. Yeah. So I like to call this hypothesis where if we're headed, this is temperature versus time. So if we're headed into an ice age and there is increasing greenhouse gases in our atmosphere that are going to cause warming, then they cancel each other out perfectly. I like to call that the Goldilocks hypothesis, right? It's just right. The problem is, according to the periodicity of changes and the comings and goings of the ice ages, the next ice age is at least 5,000 years off. So it's just not going to be here soon enough. And if it was, the odds are it's not going to be this perfect canceling out, if you will. Yeah, so are humans the primary dictator of climate change? No, but you cannot explain, that's one thing that the models are very useful for, trying to reconstruct the warming of the past century. You cannot account for that by any natural process alone. You have to have a human component in there in order to account for the ranges that we see. The greenhouse forcing component of warming is much larger. For example, some people have proposed, well, what about sunspot activity? We know that sunspots, get larger and smaller, and that increases the irradiance that we get, the radiation we get from the sun as a function of time. The changes in that magnitude are actually quite small to the changes in magnitude of the greenhouse gas forcing of our climate system. So the models, the observations are all basically saying the human component is real. It's not dictating everything about our climate system, but it's having a significant effect.
Another question is, so it looks like there's going to be a jump in the number of storms and number of severe weather events that we see. Do you expect as we move forward that that's going to be a gradual increase in these events, or do you think there's going to be a dramatic point at some place in the future where they suddenly become a lot more common?
Great question. Short answer, that's not my area of expertise. A longer answer is, I think the experts that do study this would say that there's too much uncertainty in the understanding of that now, both through models and through observations. So, if things were just continuously warming, like sea surface temperatures continuing to increase, there ought to be more intense storms marching on a year-by-year basis. But that's not what we observe, right? So it's unlikely that we're going to see things in this regular step pattern, but that there will be, decades where things are more intense than the previous decade. That's sort of the timescale we expect to see this on, as opposed to will there be what might be called a tipping point beyond which we're going to see more intense storms. I think we won't see a dramatic change at any one point. I think it's going to be a more steady progression of more increased intensity of storms. That's, at least as I read the experts such as Kerry Emanuel, who gave a couple of hot science cool talks some years back at MIT. He's an expert on this, and if I've recalled his work correctly, I think that's what we're looking at going forward.
So I have a great question here that's more personal. What motivated you to begin researching what you're doing today?
Well, so I didn't even really talk about a lot of my research, which has to do with the tree rings, has to do with cave mineral deposits called speleothems. Just like tree rings, there's evidence encoded in these mineral deposits, like stalagmites that form from dripping water in caves. And they grow unlike trees that go back 500 years, 1,000 years. We get really excited if we find a tree that's 500 years old in Texas. Like, let's go have a happy hour. A cave mineral deposit can actually cover 30,000 years in something that's just 30 centimeters tall. They're remarkable records of past climate. And I got interested in them because I had started out studying water itself, water quality, and water resource changes through time. And I kept thinking, I come to this aquifer every year and I sample it on a seasonal basis, but I have no feel for how things are changing on a longer time scale. And it's the longer time scales, these geologic time scales, that can really make a long-term difference and give us an understanding of what the system was like before human impact. And it's really important to have that baseline of these changes to our climate system prior to when humans were perturbing it, because that will help us know the changes that we're seeing today are in fact due to a departure from that natural variability. So I do this in caves in Texas and other parts of the world, and I got started in it because I was sampling modern water in a cave, and I was thinking, how can we come up with longer timescales? And I was being so careful in the cave, sampling that water, and I was crouched down, and I had kept looking behind me because there was a stalagmite, and I didn't want to sit on it because that might stop it from growing. So I was being really, you know how they say, good ideas don't come up and bite you on the butt. Well, in that case, it literally did.
Okay, so here's a really important question. And that is, what can we do to convince those who may not believe in the consequences of climate change or the science behind it that action needs to be taken?
Well, thanks for that question. That's one of the reasons I really tried to spend some time talking about the economics here. I think it's really important to consider these economic costs fully, not just loss of actual property, but loss of ecosystem services, how our world will change. Because I think for a lot of people, it's that bottom line that often wakes them up. And I think if we can make a really strong case, and there are some economists working on this, there's Sheila Olmsted here at the University of Texas LBJ School, who's an environmental economist. This is I think, one example of some really important work to show people that this will affect all aspects of our society. This is not just something that's going to change the weather a little bit, that it's going to affect our bottom line, that it's going to affect public health. And I think once people start seeing the many different ways that this will affect us, it moves just beyond the realm of science. And I think that's very important. And I think one way to also achieve this is through something you said very generously about the work we're doing at the outset of public engagement in science. There are simply not enough people engaged in science, right? And unfortunately, we've had a lot of hard lessons about this in the past several years. It's about climate change, it's about evolution, it's about this. I'm just trying to find the words. I know the word, but what I'm trying to do is politely say, I just don't understand. It's one of the remarkable achievements of medical science is that this vaccination was developed so quickly, and it's got it under control to some extent. The fact that we're here tonight tells us we're not all the way out of it. But boy, what a great endorsement of the wonder and ability of science to make our lives better. And yet, there's so many people who can't accept it and can't understand it. And that's what we're trying to do with Hot Science Cool Talks, to make everyone engaged in science.
Okay, you didn't really mention it so much, but what actions are being taken to try to mitigate the effects of climate change right now? What's going on that we should be excited about?
Well, I talked about what should be happening, I think, at the state level that's not, but I'm also happy to report that a lot of municipalities are more agile, more facile to make changes. And a lot of municipalities, even in the state of Texas, are doing some very significant things. Austin itself has a 100-year climate plan, right? So it's actually making use of climate model projections to look at what the future is, to make sure that we have enough water, for example. There are the international meetings that we have. There's the last one, the COP26 in Glasgow last November, in which all the countries of the world got together to try to iron out how can we move forward? How can we make reparations for the countries that have had so little input into the climate change because they don't have a big industrial complex, right? So the poorest countries in the world are actually bearing the brunt of what the richest countries of the world make up only 10% of the population, but they're responsible for half of the carbon emissions into the atmosphere. So I think we need to do things on many fronts. One is multinational accords, right? The other is individual governments also need to make changes. This has to happen at the corporate level, and it has to happen at the individual level as well. right? And we often hear that it's just, it's too hard, don't bother. Well, if a critical enough mass of people in the world are pessimistic about this and say it's not worth doing anything, then we know what the outcome will be. It won't be the good outcome. If enough people in the world are optimistic that there's still every reason to expect that with reasonable actions by a large number of people, we can affect a significant change, only then is the opportunity. It's not a guarantee, but there's the opportunity for a positive outcome. So for me, the biggest thing I would say is that we have to be optimistic.
I'm going to let that be the final word. And I want to thank you for a truly inspiring lecture. Thank you, Jay.
Thank you.